Hello once again. In this video, I'm going to be exemplifying the usage of the tab Sediment inside of the app River Analyst. As you can see, I have the tab here called Sediment, which performs grain size analysis from sieving datasets. My app is already running in my local port, as you can see already. So let's just refresh to be sure that I am already here. Perfect. Now, it is important to note that if you're not using the template that we provide in the GitHub repository, more specifically in the directory static/examples, then you need to provide the parsing information necessary for the app to read your data set, to read your files. And as you can already see, there are a bunch of fields here which are necessary to be filled correctly so that the app can parse files which are not our template. So let's take a look at our template here, and then you'll understand why of these values here, which are by default for our template, but can be changed to meet your data set. So for instance, this first field regards the table header, and that refers to the number of rows that you have as header before you have actually the sieve sizes and the class weights concerning the sieve sizes. So in our case, we have 9 rows, and that is exactly what we have here, 9 rows. Moving forward, this field here regards the grain size column index. So in Python, and also in this app, because it's based in Python, everything here, the indexing starts with 0. That means that the index number 1 refers to the second column, and that is exactly what we have here. Our sieves are in the second column. In this field here, we have the class weight column index, and once again, the number of the index here is 2 because the class weights are located in the third column. Here, why is it 16? Because this is the number of rows that contain sieves, okay? So in our case, we have 16 because we have followed the Wentworth scale, and we have gone through all the different sizes, grain sizes up to clay fractions, and for this reason we have 16 sieves, but you can have more or less, so just enter here the number of them. Oops. It's just... Okay, wonderful. Then here, what's important to note is that this point is actually not denoting decimal separation, but it is separating the index which refer to the row index from the index which refers to the column index. So 2.4 refers to the third row, the fourth column. And what is it here that we should pay attention? That is the porosity. So this is the index that refers to the value of the porosity. Now, I'm not going to go into details, but these you should leave as is, or just neglect if you don't have a porosity calculated with cutting edge methods that use free scores. So in the home tab of our app, we provide more information about how to derive these porosity values based on free scores with a method so-called as structure from motion. And in our case, as you can see here, why do we have this 2.4? It is because it's located, our porosity is located in the third row and then in the fifth column. Moving forward, here we have 2.5, that is the sphericity index. Again, the same system concerning that indexing starts with 0 for both row and column indexing. Then we have here the latitude index. As you can see in our template, that is exactly the 6th row and the third column, which is why we have here 5.2. So the index number 5 for the rows and the index number 2 for the columns. Then here we have the longitude, and then the sample name, the same system of indexing, and finally the sample date. What is important here is to put the projection that these coordinates are. Otherwise, the app's not going to locate your samples correctly in point map visualization that is prompted once you click in Run Analysis. And very important also is to put your projection in EPSG number. So always EPSG and then the number of the EPSG. So now we can drag and drop our samples. I am here uploading 2 samples from the in-river. And once you do that, you can run analysis. And as you can see, our samples were taken here from this gravel bar in the in-river in Bavaria, Germany. Here you can filter your samples, you can see them in a map, and then you can take a look on the grain size distribution curve, have a look on the overview of the different characteristic diameters, and also filter and take a look on the statistics of these parameters for each of the samples. Of course, you can always decide which samples to keep, which samples you don't want to look, and to make comparisons and so on. What is very important also is to click here to download summary statistics, because with that you find a gigantic table with a bunch of statistical parameters that are listed in the description of the software in the GitHub repository, from which are all derived from the sieving results that you input. What is also very important to note is that these class weights being shown here are referring to the mass of the sample that passes through the, for example, in this case, that passes through the sieve 250, but is kept and is retained by the sieve 125. So always refers, so the value of the roll of the class weight refers to the mass that passes through the grain size in the same roll, but is retained by the grain size in the next row. This is very important so that your analyses are not shifted for any reason. And that's it. Thank you very much for watching.